We will now look at applications of weak and weak star topologies in functional analysis. So we will start with reflexive spaces. So recall, V is a norm-linear space. Then you have a canonical embedding G from V to V double star. So Jx acting on any F equals Fx for all F in V star. This is the canonical embedding. This is an isometry. So J is isometry. And if J onto, then we say V is reflexive. Okay, so now we are going to characterize reflexive spaces using the weak topology. Okay, so notation. So closed unit ball in V star, V double star will be denoted by B star, B double star respectively. Okay, so the first theorem, very nice and important theorem. So V Banach, V reflexive if and only if B is weakly compact. That means compact in the weak topology. So you know that B can never be norm compact, and if you are in V star, then you know B star is weak star compact. But for reflexive spaces, the unit ball, closed unit ball, is weakly compact, and that characterizes reflexive spaces. So proof. So let us first assume that B is weakly compact. So B is weakly compact. Then J from B to BV, so J from V to V double star is an isometry, therefore it is continuous, therefore we have seen that it is also weakly continuous, and therefore JB is weakly compact in V double star. Continuous image of a compact set is compact, that's all. Okay, so then if it is compact in the weak topology, then it will be compact in any smaller topology. So this implies JB is weak star compact. Weak star topology is Hausdorff. Compact subsets in a Hausdorff space are closed. So JB is weak star closed. Therefore JB equals JB closure in the weak star topology. But we saw this result in the previous session, that this is nothing but B double star. So JB equals B double star. So J is onto the unit ball to the unit ball, and therefore it is onto from. So this implies J is onto. Because if it's onto on the unit ball, it will be onto on the entire space. So this implies V reflexive. Okay, so now let us do the opposite thing. So V is reflexive. That means the weak and the weak star topologies on V star coincide. Therefore, by Banach-Aloglu theorem, B star is weak star compact, that is weakly compact in V star. So if B star is weakly compact, by previous arguments, this shows that V star is reflexive by the first part of this theorem. If V star is reflexive, then this implies that B double star in V double star is weakly compact. Because again in V double star the weak and the weak star topologies coincide. Therefore B double star by the Banach-Aloglu is weak star compact, and therefore it is weakly compact also. And then we have that B is nothing but J inverse of B double star, because V is reflexive, and therefore J and J inverse are isometries, so they are continuous, therefore weakly continuous, and consequently implies B is weakly compact. So J is continuous, implies weakly continuous. Okay, so B. So this proves the theorem completely. So now there are lots of nice corollaries to this result. So corollary. So V and W Banach, and T from V to W isometric isomorphism. That means T is an isomorphism. T and T inverse are continuous, and it's a 1-1 onto map, and T is an isometry, and therefore it preserves the norms. Then, so if V is reflexive, then W is also reflexive. Proof. If you take BV, the closed unit ball in V, and BW, the closed unit ball in W, then T of BV equals BW. Now V reflexive implies BV weakly compact, and T is continuous, and therefore it is weakly continuous, so BW is weakly compact, implies W reflexive. Okay, next corollary. V reflexive Banach space and W closed subspace, then W is also reflexive. So proof. So what is the weak topology on W is nothing but the weak topology on V restricted to W. So check. We will do this in the exercises, but I would recommend that you check it yourself. Just a simple consequence of the Hahn-Banach theorem, because every continuous linear functional can be extended to the whole space. So you can check that the weak neighborhoods are precisely the weak neighborhood in V intersection with W. Okay, so that is all that you have to show. And therefore, if you have, so we have B. What is the closed unit ball in W? This is nothing but the closed unit ball in V intersection W. So W is closed and it's a subspace. So it's a closed subspace, implies weakly closed, and BV is weakly compact. So BW is also weakly compact, implies W reflexive. Okay. Next corollary. V Banach, then V reflexive if and only if V star reflexive. So proof. So V reflexive implies V star reflexive. Already done. Why? We have seen this, namely if V is reflexive, then B star is weakly compact by the Banach-Kaloglu theorem, because the weak and weak star topologies are the same, and therefore if it's weakly compact, we already showed that V is the space is reflexive, therefore V star is reflexive. So V reflexive implies V star reflexive, we have already shown. So now let us assume V star reflexive. So this implies that V double star is reflexive by this argument, and JV contained in V double star is a closed subspace. So by the previous corollary, we have JV is reflexive, and this implies V is reflexive since J from V to JV is an isometric isomorphism. Okay, so that proves. So V is reflexive if and only if V star is reflexive. Okay. So for instance, we know that L1 is not reflexive because L infinity star is not L1. But then, so L1 is not reflexive, so L infinity cannot be reflexive either. Okay. So next corollary, V reflexive and K contained in V closed, bounded and convex implies K is weakly compact. So it's not just the ball which is weakly compact, every closed, bounded convex set is automatically weakly compact. Proof. So K is bounded, so this implies that K is contained in some m times the unit ball. Okay, so m times the unit ball, this is weakly compact because it's just scaling the unit ball, and since V is reflexive, and K is a closed convex set, so it is weakly closed, and therefore a closed subset of a compact set is compact in a Hausdorff space, therefore K is weakly compact. So that proves that result. Okay. So proposition. Let VW be Banach and W reflexive. Let A, which is an unbounded operator defined in V taking values in W, be closed and densely defined. Then, so it's densely defined, so the adjoint is defined, so then A star is also densely defined. So we made this remark already, A star need not be in general densely defined, but A star is always closed. So A is densely defined, you can define A star, and A star is closed. This is what we know. But if A is closed and densely defined, then A star is densely defined, and you know A star is closed, so A star is also closed and densely defined. So proof. Okay. So what do you want to show? So let phi, we want to show that D of A star is dense. So we are going to use the Hahn-Banach theorem. Let phi belong to V double star, W double star, sorry, such that phi equal to 0 on dA star. To show phi is equal to 0 everywhere in W star. Okay, W double star. Okay, so something which vanishes on a set vanishes everywhere, and therefore you want to show that it is. But W is reflexive. So this implies that there exists a Y in W such that phi V, this is in W double star to W star, is equal to Vy, this is in W star W, for all V in W, W star. Okay, this is the meaning of reflexive. So that means every functional occurs as an evaluation. Okay, so to show y equal to 0, because phi is essentially determined by y, so we want to show that phi equal to y equal to 0. Okay, to show y equal to 0. So what is given? We are given the wy equal to 0 for all w in domain of A star. Okay, so if y is not 0, then 0y does not belong to the graph of A. 0 is in domain of A, and if 0y has to be in graph of A, y has to be A of 0, that is 0, which is not true. So 0y does not belong to the graph of A. Okay, so y is in W. Okay, so it's not in the graph of A. Okay, so therefore by Han-Banach there exists Fv, and graph of A is closed. Remember that is given to you because A is a closed operator, that means graph A is closed. So there exists Fv in V star cross W star. So this is closed and this is contained in V cross W. So the dual space is V cross W star, which does not vanish on 0y. So that means such that Vy is not 0. Okay, but Fu, this is from V star V plus VAU this in W star W is 0 for all U in dA. Then what is this mod VAU? This is less than or equal to norm F into norm U, and this implies that V belongs to domain of A star and F equals A star B. But if V is in domain of A star, this implies Vy has to be 0. That is a given condition, which is a contradiction. We are given that Wy is 0 for all W in dA star, and therefore this is a contradiction. Okay. So this proves this theorem. So this is a contradiction. So Y has to be 0. That means dA star is dense. Okay. So now let us assume that V and W are both reflexive, and V and A from dA contained in V to W is closed and densely defined. Then we just saw that A star, which is defined on dA star contained in V, W star going into V star. Okay, and this is defined because A is densely defined. This is also closed and densely defined. This is by the previous proposition. So A double star from dA double star contained in V double star going into W double star is defined because A star is densely defined, A double star is defined. But we are going to take V reflexive, so this can be identified with V and this can be identified with W. So we consider A double star defined on dA double star contained in V going into W. So we can consider it like this, and because we can identify being both all spaces being reflexive, V double star can be identified with V and W double star can be identified with W. So then the theorem nice important theorem. So let V and W be reflexive Banach spaces, and A from dA contained in V going into W closed and densely defined. Then A double star equal to E. So these two mappings are the same. So when do you say two unbounded operators are the same? You have to show that the domains are the same, and you must also show that the action on each member of the domain is the same. So proof, need to show dA double star equal to dA, and for every u in dA we have to show A double star u equals AU. That is enough to show graph of A double star equals graph of A. Because what is graph of A? It is a domain, all the first coordinates are in the domain and the second coordinate is the action, and these two are the same. That means the mappings are one and the same. Okay, so recall you have this script J from W star cross V star to V star cross W star. J of Vf is minus Fv. And then we saw that J of GA star, this was already shown, is nothing but GA perp. So GA double perp will be J of GA star perp. Okay, so what does this mean? So what is GA double perp? This is J of GA star perp. So this should consist of all elements VW in V cross W, which kill every element of JGA star. Now what does JGA star looks like? So J of GA star will be looking like minus A star phi in dA star. Okay, so that is J of GA star. So we want VW to kill all of them. So we want such that minus A star phi V. So this is in V star V plus phi W, and this is in W star W equal to 0. And this should be true for all phi in dA star. Now this relationship tells you that mod A star phi W is phi W, which is less than or equal to norm W norm phi, and therefore this tells for all phi in dA star, A star phi V, sorry, and this tells you that V belongs to D of A double star, and A star V equals W, A double star V, sorry, equals W, and therefore so keeping that in mind, this is nothing but, so V must be in dA double star so this is all VW in dA double star cross W such that dA double star this set A double star V equals W, and that is precisely graph of A double star. Therefore, graph of A double star equals GA double perp, but you know double perp in the base space is nothing but the closure, so GA closure, but A is a closed operator and therefore this is equal to GA, and that completes the proof of the theorem. Okay, so that is, so we will next look at separable spaces in the next session.